we covered the main thing. We said that we have to have feedback, and we were able to design a circuit that has a feedback and it remembers something. Okay? But it's hard to express this remembering as something that we think of memory. See, memory means you write something at a certain time, and then later on you can retrieve it, you can get back to it. So timing is important in remembering. Okay, something like, at this time, remember this. At a later time, override it. And then remember this instead. My circuit, the circuit I showed you so far, doesn't have that timing concept. It doesn't have timing. S and R come in and change the output, whatever. Okay? What I'm going to do is I'm going to add the concept of timing to it. I bring in a new signal in addition to S and R and call it clock. Okay? But then this clock is a signal that if it's 0, okay, S and R, the external S and R, do not arrive at the internal S and R. And we have already shown that if S and R are 0, Q plus remains the same. Okay, no change. And therefore, if S and R are 0, 0, whatever Q was stays the same. Until, listen, until means what? Time. Until my clock goes from 0 to 1, telling, okay, at this point in time, take the external S and R, propagate it to the gate, affect the output, and wait until the next time. What it means is, at this time, take S and R, propagate it through, and wait until the next time. That means the next clock. And therefore, I have clock pulses. During these clock pulses, I tell this memory element to look at the input, affect the output, wait until the next clock. Don't do anything until the next clock. I just added the concept of timing to this little thing. And I control the timing by these clock pulses. Nothing happens outside of these clock pulses. Okay? What do I call this? Why not a clocked SR-Latch? An SR-Latch that is clocked. And what is the clock? Clock are pulses during which the latch looks at the inputs and then only then affects the output. Let's write the transition table. The transition table says if clock is 1, active, okay? If SR is 0, 0, stays the same. 0, 1, reset it. 1, 0, set it. 1, 1, don't touch it. 1, 1, you are not supposed to give it 1, 1. You can't give it 1, 1 if it's outside the clock. But then during the clock, you cannot give it 1, 1 because it loses the memory. And so this is invalid. And then what if clock is 0? Clock is 0. The output remains the same and S and R can change to whatever they want. They actually have no relevance to what happens to the inside S and R of the latch. This is called an SR-Latch, a clocked SR-Latch. See, I started with that little feedback and said that there is some memory. Okay, I haven't really convinced you that this is a real memory. It remembers something. I have said there is a signal S, there is a signal R, and then during the clock, S and R are going to be looked at. And then if the S has a positive pulse in it, on it, then you are setting. If R has a positive pulse on it, you are resetting it. Now, the definition changed to the same thing, except that this happens during the clock. Okay? Or you can say when the clock is 1, if only when the clock is 1, if S is 1, then the Q becomes 1. If the clock is 1, if R is 1, then Q becomes 0. If clock is 0, don't do anything. I'm going to write the very long description in a second. There's also another problem. I don't like this S and R thing. I like my memory to remember something. Remember at least that the last time I gave it a 0 or I gave it a 1. Let's do the very long description and then we go into the changing what it remembers. The very long description goes like this. Okay. Always. Let me start with the module itself. Module clocked SR-Latch. Input SR clock. Output, because I'm going to be using always the statement reg Q. This time I'm also going to give it another output Q bar. That's if you have to have it. Okay. Obviously you see that I'm not going to set my Q bar inside an always statement because it's not a reg. Then I have always at clock SR begin. Okay. If clock equal 1 tick B1. Okay, just like to use 1 tick B1, you could just say 1. Begin. I do this so that this if block is where my clock is 1. That means I don't get into this if the clock is 0. Okay? And if I don't get into this, this is end. That means my always statement just exits. If I come in and my clock is not 1, I just exit completely. Okay? I only go into the block that checks the clock only if the clock is 1, obviously. And this is end module. Yeah, in some areas of the screen it's hard to write. Anyway, in here, if set Q, okay, becomes 1. Okay, before I showed you Q equal to 1. There is a rule in Verilog and it says sequential circuits, when you are setting something to the output of a sequential block, which is this latch here, use this symbol. This is called blocking, which we have been using before. This is called non-blocking, which I'm going to be using from this point on. Why did I use non-blocking in the previous example I showed you for the latch? Well, let me tell you this. It says logic elements or logic component, combinational parts, always are are blocking. Okay, use blocking assignment for the for the combinational parts. For the sequential parts, it says if they are the non-transparent, which I haven't shown you yet, definitely use non-blocking. The structures I'm talking about are transparent blocks. That means during the clock, the input changes the output. So transparent blocks, which is this component, is somewhere between combinational and the non-transparent blocks, which I'm going to be showing. And therefore, you can either use blocking or non-blocking. But now, since we are getting into the non-transparent block, which I'm going to say show you in a few minutes, definitely use non-blocking. Why is this transparent? I will talk about it in just 1 minute. If S is 1, Q becomes 1 tick B1. Else, if R is 1, Q becomes 1 tick B0. What if S is 1 and R is 1? I'm not handling that. What happens if S is 1 and R is 1? Both of them are 1 simultaneously. I'm actually seeing only S is 1, and I'm setting my Q to 1. So I'm not handling that invalid state. I could say if S and R are both 1 during the clock, raise a flag saying that you're doing something bad. Okay? Why do I call this one a transparent latch? I'm calling this one a SR clocked latch, and this is a very long description of it. This is a transparent latch. Transparent means this. During the time that clock is 1, the S input propagates to the output, the R input propagates to the output. That means it's just transparent. During the time that the clock is 1, this input propagates to the output. This input also propagates to the output. Just like a combinational circuit. That's why we call this structure a transparent structure. Actually, all the latches are transparent structures. Okay? All right. What else here? Well, what else? I also showed you a Q bar, which I haven't shown you the very long correspondence of it. I use an assign, and I can put it anywhere I want. Q bar equal tilde Q. That's all. Okay? Don't put Q bar inside this always statement, because that causes complications. Okay? And I could, but then code-wise, it's much easier to just do Q inside the always statement and pull Q bar outside. And as you are seeing, my Q output is reg, my Q bar is not reg. All right, this is an SR-Latch. Okay, let's go back to our story. We started with a cross-coupled latch, and then we said this is good. And then we said it remembers something, but then we said, well, the concept of timing is missing, so we gave it a clock. Something else we have a problem with, and that is, I said this before, I like to write something at a certain amount, at a certain time, and that something is remembered. Okay, I don't like the S and R thing. I like one value to be written and that value to be saved. I'm going to talk about D-Latch. Okay? And this one is a clocked D-Latch. I take that SR-Latch that you saw before. Oops, not this far, this far. SR-Latch. Okay? And then, this is something, I'm going to show you the table here. See, the table here, the internal S and R, internal S and R, and then clock. Okay? And then Q plus. If clock is 0, the internal S and R are 0, 0. Okay? If clock is 1, 0, 1, 0, 1 resets it. If clock is 1, 1, 0 sets it. Okay? And then this is Q. If clock is 1, internal SR11 shouldn't happen anyway. Okay? I'm going to do this. I'm going to add an inverter here and bring my D input and then call it the D input or data input. I'm going to take that D, invert it, and put it into the lower AND gate. Okay? Then I claim that I have not limited this structure or the data that applies to this structure. Because if the clock is 0, the internal S and R are 0. Okay? The internal S and R are 0. And therefore, it does take the 0, 0 that it should be taking. If clock is 1, if the D input is 1, the internal S becomes 1, the internal R, because there is that inverter there, becomes 0. Okay? And therefore, if D is 1, you are getting this situation that causes the output to become 1. If D is 0 and the clock is 1, okay, if D is 0, this becomes 1 and clock becomes 1, and therefore S becomes 0, R becomes 1, which means this situation here. What am I not allowing on S and R, the internal S and R? What I'm not allowing is 1, 1 because of this inverter. This inverter never lets the S and R to be the same. They're complement of each other. But then the 0, 0 case is, which this inverter does not allow, the clock becoming 0 allows the internal S and R 0, 0. That means the output retains its value for as long as clock is 0. And therefore, this table covers all the valid situations that I want to put on S and R. This becomes my transition table. And I'm showing that during the clock, D goes to Q. During the clock, D goes to Q. That means anytime clock arrives or clock becomes 1, the next state, the next output becomes the present Q. And then this is the characteristic equation of this D-Latch. And D for data. This is a D-Latch. I'm just adding an inverter, and then the situation of S and R are not allowed anymore, and I have one input, and that one input is saved in the structure, in the output. At this time, it saves it there until the next time. Okay? And therefore, I built a unit that takes some tiny little information, that tiny little bit information. It saves it at a certain amount, at a certain time, it saves it, and it keeps it for the next time. And therefore, I do have a memory element. What if I need 16 different things to be saved? Well, connect 4 of these together, and therefore I have between numbers 0 to 15 to save. And this is the symbol for it. Okay, the symbol says when I get a clock, the D input goes into the output. This is also a transparent latch. Why? Because when the clock is 1, the D input just propagates through. So whatever change happens on D happens on Q. Okay? That's why we call this one a transparent latch. Let's do Verilog module D-Latch transparent, if you want to say that. Input D and clock. Output reg Q. Okay? Always, if D changes or the clock changes, okay? If D changes or the clock changes, Q gets D. So, okay. I don't need begin and end. All I'm saying is when D or clock change, flow begins. When flow begins, if clock is 1, whatever is on D goes on Q, transparency. When clock is 1, whatever is on D goes on Q. Okay? If I come into this, clock is 0, then this if is completely skipped, and then what happens? The output retains its old value. That means this is a latch. It remembers something. What else can I say about this? When D changes, let's say D is 1, and then let's say clock changes. Clock changes and flow begins. Flow begins, the value of D goes into Q. Okay? And while clock is 1, if D changes again, then the flow begins again and finds clock equal to 1, and D also affects the output again. What it means is during the entire time that clock is 1, when D changes, flow begins and D is put on the output. Again, I'm talking about transparency. Transparency is good, but in this particular case, it will cause us problem in some cases. All right, so we have covered starting cross-coupled NORs, and then SR-Latch, clock SR-Latch, and now we talked about D-Latch, and we are quite happy. Okay, we are quite happy because we are saying that we finally have a unit, a simple circuit that remembers a bit. a bit value, either 0 or 1, during the time that I gave it the clock. Okay, then we continue with the exercising this next time.